and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion science and engineering. I'm Ekaterina, and I would like to introduce our speaker today, Nicola Isernia. Nicola has got his Master of Science in Electrical Engineering in 2018 with a thesis investigating the relative effect of 3D magnetic fields to do non-axisymmetric structures in tokamak discharges. Right after that, he spent some months at the Institute of Plasma Physics here in Prague, where he provided support for the design of compass upgrade tokamak. And now Nicola is doing his PhD at the Information Technology and Electrical Engineering School at University of Naples, Federico II, since November 2018. His research interest is mainly devoted to the electromagnetic interaction of fusion plasmas with surrounding structures. And up to now, he has been mainly interested in the problem of the eddy currents and electromagnetic forces generated in tokamaks during fast transients, both by means of numerical tools and analytical models, and also analyzing present-day disruption experiments. So without further delay, I give the floor to Nicola and I mute myself. Please.
Thank you, Ekaterina, for the nice introduction. Can you hear me, right? Okay, perfect. And thank you for the introduction. I can start directly at this point. I would just like to acknowledge my tutor, Professor Fabio Villone, and also my other colleagues, Claudio Serpico and Valentino Scalera, which worked me on the topic I'm going to present you today. Then let's start. Okay, I will just provide some motivations for investigating the energy balance during disruptions. There were previous FusionEP talks about this, also from Ekaterina and from Javier Artola, so I will be fast really on this. And then we will try to address some important question which is of interest for disruption in tokamaks. Namely, which are the energy exchanges, which are the energy fluxes of importance during the current quench phase of a disruption, which we'll define in a while. So we will try to understand which is the role of electromagnetic conducting structures surrounding the tokamak in these tasks, these specific tasks. I provided here some references which you may be interested to read, and I can share with you. So you all know that due to these hard to predict fast transient events, there are some limitations in the operation of tokamak, and so in the possibility of having experiments. In particular, you cannot go above some threshold limit for the average density within the plasma, or you cannot have an arbitrary plasma current due to some threshold on the safety factor at the edge of the plasma column. Or moreover, for elongated plasma, you may have some vertical instability taking place that leads you to the plasma hitting the wall and the sudden loss of your thermal energy. Any of these events and other instabilities may generate a disruption, which may have several consequences. In particular, there's in general a sudden and rapid thermal energy loss, and moreover, the currents decrease very rapidly, generating eddy currents in vessel structures, which generate huge forces on the structures, which may damage even your device. So let's just move fast on this. I would just like to remind you that in general, due to the overcome of some operational limit, or due to some instability, there is a sudden loss of the thermal energy within the plasma, maybe through radiation. This is the case, for example, for density limit disruptions. And after this, there may be a current flattening. I mean, the density profile of the current within the plasma column may flatten down due to the thermalization of the plasma itself. And then due to the increased resistivity, due to the low temperature which the plasma has reached, there's a sudden current decrease with a very high decay rate, which is generating great eddy currents in the vessels, in the surrounding vessel. And there may be even for strong electric fields generation of runaway electrons, so electrons can be accelerated up to relativistic velocities. But we won't be interested in this throughout this talk, since this would really complicate quite much the picture we are going to give. So we, as hinted, we would really like to understand, while it's quite widely accepted that all the thermal energy is released during the thermal quench phase, then we shall agree on which is actually the which are actually the plasma losses during the current quench phase of a disruption. And in order to grasp this, we consider a simple first principle scheme now. So namely, we take into account the main energy sinks for our problem, the electromagnetic one, then the kinetic energy of the fluid, and the internal energy, so the thermal energy of the plasma. And if we account for the balances of these, so the evolution equations for these three energy density sinks, we may sum up that to just check that the total energy is conserved, of course, as long as nuclear reactions do not take place clearly. And then this is, we can neglect electrostatic energy, as you know already. I suppose you are familiar with MHD formulations. And so the picture is pretty much the one I portray here. There are three energy sinks. They may exchange energy between each other through some threads, which are also highlighted. So the magnetic energy can supply both a kinetic energy for the fluid or an internal energy, really. And I would like just to stress that at this stage of energy balance, we don't really even to take into account any constitutive relation for the electric current. We may just be well with this with this scalar product of the electric current with the electric field perceived by the fluid element in its motion. And due to our typical parameters of operation in fusion plasmas, so the relatively low densities, the relatively high temperatures, and strong magnetic fields, actually the kinetic energy sink is in a sense negligible as compared to the magnetic energy one and to the thermal energy. So we may take into consideration an even simple picture in which the magnetic energy can only be exchanged to internal energy by some mechanism which may be the Joule losses, for example. And so within this picture, let's try to even simplify more the picture, taking into account that we are here in a torus-shaped geometry, and so that we may really decompose our problem, taking into account poloidal magnetic energy and the toroidal magnetic energy. And since really we are neglecting the energy related to the electric field, this provides us with a clear cut in the Poynting vector theorem, in a sense, meaning that actually the variation within a certain volume of the poloidal magnetic energy can be expressed by a certain component of the flux of the Poynting vector through the boundaries of this volume, and then the volume integral of the cross product of the electric field, of the toroidal electric field and the toroidal current density. We can do the same also for the toroidal magnetic energy. And what is important here to underline is that in general, in tokamak devices, the losses related to poloidal currents are quite small. You may think that in a really simple high aspect ratio circular cross-section picture for poloidal beta equal to 1, you would not even have a net poloidal current in a sense. So in general, this volume integral here is quite small. And what does this mean? That you have one component of the flux of the Poynting vector, the one which is related to the poloidal electric field and the toroidal magnetic field, that is perfectly compensating the variation of toroidal magnetic energy within the control volume. We will take throughout this talk as control volume the volume enclosed by the first wall, so the volume where the plasma may live in. And so we have this clear compensation of one component of the Poynting vector flux and one of the component of the magnetic energy. And moreover, the expression for this flux of toroidal magnetic energy is pretty simple. It looks like a circuit theory expression in which you have the poloidal current linked, in a sense, to the boundary of our control volume, and the toroidal flux, which is linked to the cross section, to the poloidal cross section of this first wall volume. On the other end, for the poloidal magnetic energy balance, we will need, in a sense, to know something about this energy exchange term, and we will need to evaluate later this term numerically. So, as important results, we may already simplify the overall, the total energy conservation equation, in a sense, because two terms are compensating each other. And so you see here that you may take that a variation of the total energy is in a sense related to an influx of poloidal magnetic energy or a plasma loss. Of course, here you don't see the toroidal magnetic energy term and the related Poynting vector flux term, because they compensate each other. And in particular, we can apply this scheme to the current quench phase of a disruption, where we assume the thermal energy is more or less fixed because we lost all of that during the previous thermal quench. And so actually integrating through time, the expression for the losses during the current quench turns out to be particularly simple, because what is that you can really lose during this phase is just the poloidal magnetic energy within your control volume and any poloidal magnetic energy which is getting inside, which is represented by this second term here. And then you would really need just a simple, relatively simple, I would say, evolutionary equilibrium model in order to get an estimate of the energy losses during the current quench. And so we will apply in a while this scheme by an evolutionary equilibrium model. Let me first just give you a toy model to understand the importance of the surrounding structures. I take here a nia-aspect ratio tokamak with circular cross-section, and you see the expression for the poloidal magnetic energy is particularly simple. This is related, of course, to the total plasma current and to the internal inductance of the plasma. Moreover, there's some energy which is accumulated between the plasma and the first wall. And so this is accounting for this extra energy term, in a sense. And moreover, all the energy, poloidal magnetic energy flux that may happen through the boundaries of your first wall volume, it can be simplified to this expression, which is also quite, in a sense, simple to understand, as you see these are products of the plasma current with voltages, because these are time variations of fluxes, both due to the plasma current variations or the total toroidal wall current variations. Okay, so in this relatively simple, with these relatively simple formulas, we may apply the previous scheme I showed you to get some synthetic formulas. And in particular, you may consider the energy loss, the energy loss during the current quench in two limiting cases. Some words are due. How can I estimate really the total toroidal vessel current which is setting up during the current quench? In a simplified scheme, you may set up this simple dynamic equation where tau 0 wall is an electromagnetic time constant which is solely related to the wall geometry and conductivity. Here sigma is the conductivity of the wall, d wall is the thickness of the vacuum vessel. And so by this simple model, you may take the two limiting cases to be the ideal wall approximation, in which you see that the current quench time is really much smaller than the electromagnetic time constant, and then all the current that the plasma is losing, in a sense, is raising in the vacuum vessel surrounding the plasma. And so that you see that an eventual plasma energy loss you may have is solely related to the variation of the poloidal magnetic energy within the vessel. And on the other end, you may say that the current quench happens on a time scale which is much higher than the electromagnetic time constant. And in this case, the energy available for conversion to thermal energy, and so to plasma loss towards the first wall, is all the poloidal magnetic energy which is related to the plasma current in the whole space. So you see that the electromagnetic time constant of the vessel plays a crucial role in determining which is the actual amount of energy deposition on the wall, of thermal energy deposition on the wall, or radiated energy you may expect during the current quench. Please, I don't want you to think that it is good to have a really fast current quench, because this will anyway generate other kinds of problems which are related to forces, of course. So in a sense, you should find that you should avoid, of course, disruptions, but you should find a compromise, in a sense, between these constraints when you have to ramp down the current, for example. And so moving further, besides the toy model, we would like also to investigate some more realistic example. And in order to do this, we already say that we may use a relatively simple evolutionary equilibrium model. What I mean? I mean that we are discarding the kinetic energy from the picture already. Hence, we may be stay with describing the plasma just with an MHD equilibrium model, in which hence we take Ampere's law and we take a force balance between the pressure gradients and the Lorentz force. And of course, here the magnetic field is both due to the plasma and due to the currents which are circulating in active and passive conductors outside the plasma. And we already saw that here the eddy currents are playing a crucial role. And so we shall describe also the eddy currents in passive structures, and we shall solve magneto-quasi-static problems in the surrounding conducting structures. I just go fast in saying that we may solve this problem with the Karman 0NL code, or evolutionary equilibrium model, if you prefer. And we have some approximation on the plasma. We assume this is axisymmetric, so we have just to solve the Grad-Shafanov equation within the plasma. You will notice that there's a boundary condition for the poloidal flux, which is related also to the currents which are flowing in the passive conducting structures surrounding the plasma. And then you shall solve the eddy currents problem in structures, and you can do this with an integral formulation in terms of an electric potential. For example, this is what is done in Karma-Zero-NL. And you will end up with a kind of circuit equations, in a sense, in which there are some voltages applied to the structures, which are related actually to the variations of plasma parameters. For example, the plasma current or just the motion of the plasma column within your domain. So there's a coupling, of course, between these two problems. I mean that the poloid, in order to solve the Grad-Schaffranov equation, you need some information from the eddy current problem, and on the other way around, in order to understand which are the currents in the vessel, you should know which are the induced voltages due to plasma variations in the structures. So we will now apply this tool to actually examine a couple of examples on the TCV tokamak and jet tokamak, if we have enough time. And as is for TCV, I show here the geometry of the vessel and of some coils, and I also show you the position of some internal discrete coils and flux loops, so some diagnostics for measurement. And for the way they are actually installed in TCV, you may actually discretize some of the integral I presented you before, so really the poloidal magnetic energy flux, by the measurements from these coils and flux loops. And of course, these are not placed on the first wall, but close to the vacuum vessel. So we won't find exactly the same flux which is flowing, the same poloidal magnetic energy flux which is flowing within the vessel or within the first wall. There might be a difference, which is related really to the fact that there's a gap between the first wall and the vessel, and there you may accumulate poloidal magnetic energy as well. And moreover, between the first wall and the vacuum vessel, here you have also some active coils for vertical stabilization, which may provide you with further terms of energy exchange with the external environment. And so we try a simulation. And in order to set up this simulation, we take as initial equilibrium one taken from an experiment. We take from Yuki some flux maps, and we are able to recompute an initial flux map for our computations. We also cross-check that, in a sense, the simulated measurements are in agreement with the experimental ones. And then I'm not going to show you really an experiment for the rest, in the sense that then I impose some fictitious experiment which reproduces some typical behavior of disruptions. Since I'm still working on the experimental data, and also I should ask permission to show you really experimental results. Then you see between our parameters, between our input parameters for the model, we have the overall toroidal plasma current. So we are actually imposing this kind of time evolution for the plasma current. And also we are able, we manipulate some profile parameters in the relation between the toroidal current and the poloidal flux, which allow us to indicate how the poloidal beta should evolve through time, and also how the internal inductance should evolve through time. You see that here we have a relatively fast thermal quench. Then there's a period in which the current is raising up, and at the same time the internal inductance is going down. And then we have the real current quench with the quite high decay rate. of about 50 kiloampere per millisecond. So let's go to take a look to the simulation. You see here in the first instance just the thermal quench, then the current is the toroidal current density profile is flattening. I don't know if you can see really. Then the toroidal current starts to go down, and as this goes down, you will have more and more toroidal current induced in the vacuum vessel structures. Of course, the plasma current is only inside here. This is an artifact of the visualization. Also, the plasma now is shrinking while the plasma current is decreasing. Okay. And so let's look at what we are interested really in this simulation. From the one end, the poloidal magnetic energy flux through the first wall. And also we can compare this from what we would estimate with the diagnostics if we had an experiment, for example. And you see that especially during the current quench, you have a mismatch between the poloidal magnetic energy flux you will estimate by the diagnostics and actually the numerically calculated, so in this case the reference one. And as I was saying you, this is related to some poloidal magnetic energy which is accumulated in the first wall vacuum vessel gap. And we may look also at in a sense, at all the terms involved within the energy balance. You see, and this was a sort of assumption for us that we had in the first time interval the thermal quench. Here all the internal energy is lost, and is lost as plasma losses. I mean, there's no significant variation of the poloidal magnetic energy during this phase. Notice that throughout all the simulation, the variation in the toroidal magnetic energy, so the one depicted in blue here, is perfectly compensated by one component of the Poynting vector flux, and of course integrated through time. And we also show that this should happen. And then what is important to figure out here, during this current flattening, you may see that the poloidal, yes, that's okay, you have a slight poloidal magnetic energy influx, but this is anyway quite little here. I don't know if you can see it. Ah, no, sorry. You see the violet curve here, which is slightly increasing. This means that you have a poloidal magnetic energy influx here, which is anyway compensated by the variation of poloidal magnetic energy within the vessel, so that in the end you don't find any appreciable loss within this period of time. Then as the current quench starts, you have both energy entering the vacuum vessel, and the poloidal magnetic energy is consumed. And if no internal energy variation is assumed, then you will find this as plasma losses for sure. Okay. Oh, sorry. Here for the current flattening phase, I would like to come back here. Here, the poloidal magnetic energy flux is going from the plasma, from the inside the first wall to the external environment. So, and it's why you see that the poloidal magnetic energy is slightly decreasing here. But the important, in a sense, is that you have no plasma loss during this phase. Okay, we may also compare actually the losses we have in the numerical situation with the losses which we would estimate by the simple analytical formulas I introduced you before. And you see the situation is quite well described in a sense by the ideal wall approximation, in a sense, at least in the first time instance of current quench. You see also the error is diverging in a sense, because anyway, a small error on the power terms then is here integrated through time. Indeed, if you take a look at plasma losses in terms of the thermal power exchanged, in a sense, through the first fold, you see that the fast approximation, the analytical approximation in the ideal wall limit is quite good. Is quite good in describing the actual energy loss we have in the simulation. So I think there's room for showing you another similar example, this time for jet tokamak. Here also we reproduce an initial equilibrium configuration for the poloidal flux within our first wall volume by taking some data from EFIT and then cross-checking that the initial equilibrium we have gives some simulated measurements which are in agreement with experimental ones. But again, also here, we take some fictitious time evolution for our numerical experiment, in a sense. We take a relatively fast thermal quench again, and we take we consider a period in which the current density profile is flattening, and contemporarily we have an increase of the plasma current. And then we observe in particular what's happening during the current decay, during the current quench. And so I always show you an example of what's going on here. Maybe here I didn't draw actually a plasma boundary, but you should be more interested in the toroidal plasma current density profile. Okay, now you see the current quench is starting, the plasma current is decreasing. Most of the toroidal current in this case is drained from passive stabilizer rather than the vacuum vessel. So this is, of course, define the picture, and it's also some downward motion. Okay. So, oh, sorry. So the situation is pretty similar also here. All the internal energy is lost during the thermal quench, and then during the current flattening, the situation is similar as you saw before, so that during the current quench, you have a poloidal magnetic energy which is decreasing. At the same time, the poloidal magnetic energy is entering the first wall, and so all this energy is consumed and is in a sense radiated or anyway lost by the plasma through some mechanism which we are not of course studying in this simple framework. And notice also always that there's an almost perfect compensation of the variation in toroidal magnetic energy here in blue, and one component of the Poynting vector flux, the one related to the poloidal electric field, and the toroidal magnetic field here in green. So we may see that also in this case the fast approximation from analytical formulas is giving in the first time instance of the current quench pretty much good results, or at least in agreement with what we predict numerically. So I hope I was not going too fast. I would like here to recollect the key points before we open the discussion. So what we studied together today. We saw that the toroidal magnetic energy is not really much entering the picture of energy exchange term with other energy sinks, due to the fact that the poloidal current is relatively small, is not giving much losses. Then we investigated the role of passive conductors surrounding the vessel in the problem of the energy deposition on the wall and on the radiated energy during the current quench. And we also provided some motivation why evolutionary equilibrium models may be used to provide an estimate of the energy losses from the plasma during the current quench. But you may see this also the other way around. I mean, if you are sure about the losses you have in some experiment, because you are able to measure them, for example, through bolometers or other diagnostics, then you may actually check that your simulation is providing the correct losses. And so you have a way in which you will actually validate your evolutionary equilibrium simulations with the experimental data. And in the, let's say, in the next future, we are now also investigating some experiments within this scheme. We would like to extend this comparison to other machines and other experiments. And another interesting thing we would like to do is really to study how the runaway electrons enter into this picture. This is particularly interesting because this would add an extra energy sink within the initial simplified picture I show you at the beginning of the talk. And it would be particularly interesting since it is quite common that during the current quench, due to the strong toroidal electric fields generated due to these fast variations of the plasma current, some electrons are accelerated up to relativistic velocities. And so how this enter into this picture. It would be good also to investigate if the picture I show you about the compensation of toroidal magnetic energy with one component of the Poynting vector flux keeps to be valid also in a situation where halo currents are present. Of course, if the poloidal halo currents will be strong, then we should expect there's some exchange term with other energy sinks will be present also here. But we are still working on this, and we would like to investigate this in the near future. So I hope I provided with some simple tools, and I hope also to have stimulated some questions, because I was probably fast on many points. So thank you everyone for your attention, and Ekaterina, any comment is welcome.
Thank you very much for the very interesting and detailed talk. Now the floor is open for questions.
Thank you, Nicola, for the presentation. I have a very non-specialist question. I mean, so the plasma is treated with MHD during disruption. And is it, so it's a Grad-Shafranov equation or something else? So it's a...
Yes, we are actually, since we are not interested really much in the kinetic energy, we thought it was good, I come back here, to just assume that at each time instant of our simulation, we are in a situation of magnetohydrodynamic equilibrium, really. So in a sense, this is a constraint on our dynamic simulation. Of course, in this way, we are giving many physics as an input. I mean that in order to solve the Grad-Shafranov problem, we are really imposing as an external input, which is for example, the poloidal beta or some other shape parameters, which relate which are parameters that gives us a parameterization of the toroidal current as a function of the poloidal flux. I don't know if this answers your question.
Yeah, because I wanted to ask the next question, if I'm allowed, because these are axis symmetric equations, and how it's in reality, does one really can assume that plasma kind of disrupts axis symmetrically? So this is the main, I had this question quite a long time, and I don't find, because somehow, I mean, I think although its disruption is very fast for, let's say, man eye, but in reality for instability it is very long time. So this instability can a microsecond time scale. So how good is any evidence that this is correct, or is some evidence that one has to go to let's say non-axisymmetric consideration of the MHD?
This is an interesting question. Thanks. I would say that really you may evaluate in which experiment you are well within the axisymmetric assumption or not. I mean, for example, in JET, you have magnetic measurements located at different octants of the vessel, and then you may check out whether these are giving you the same readings or not. So if these are giving you the same readings, you are in a more or less axisymmetric situation, and then it's this scheme makes sense, in my opinion. Of course, whenever you see that from the magnetic measurements you have different readings at different octants, then you should go probably to more sophisticated models, or maybe you could even stay with MHD equilibrium, but you shall drop out the axisymmetric assumption, in a sense.
Okay, I understand. Thank you very much.
Thank you. Thank you.
Anyone else came up with any question? Well, if not, then I would like to thank you again for the great talk, and thank you for joining us today. This is an official end of our webinar.